Hello universe. Today we're going to be trying to describe this theorem about the change of variables formula. And this is my friend Lavish. You want to introduce yourself?
What's up? I'm live.
So Lavish doesn't have any experience with college math. What is your experience with math?
Just all the way from grade school to high school, really. That's it.
Okay.
Yeah.
Just
Probably the top I went to is algebra. So
okay.
That's it.
Cool. Yeah. So that shouldn't be a problem. So hopefully we'll be able to explain this theorem. You shouldn't need a math background. Like, I feel like math at its core needs to be simple, and hopefully we can explain this theorem without needing you to have any of those, like any of the classes that would normally you'd have to take to understand it.
Okay.
So yeah, let's try this out.
Okay. Alright, I'm gonna take a seat. Fire away.
Okay, so let's begin by talking about Rn, the symbol Rn here, okay?
Okay.
So, what is R? Have you seen this symbol before?
I've never seen that.
Okay, so what this means is it's the real numbers, okay?
Okay.
So just think of the number line, all the numbers are here, right? So any point on this number line, I can use like a base 10 number system to describe where this is. Let's say this is 0, okay? And then at any point on this number line, I can describe it within a base 10 number system. So maybe this is like 3.157239026, etc., right? So all the real numbers are going to look like this. They're going to be describable as basically an infinite decimal, right?
Okay.
And this is the line of numbers. Now, if I look at R2, R2 is actually two-dimensional space, a plane. And I form it by basically taking two axes that are both the real copies of the real line, and then I kind of stick them together with something called the Cartesian product, and I get an entire plane. Okay?
Okay.
And every point on this plane can be described in terms of its coordinates as, let's say, this x coordinate and this y coordinate. So any point on the plane, I can describe it as with two real numbers. Namely, how far is it to the right of 0 with respect to this x-axis, and how far above 0 is it with respect to the y-axis. So every point can be found on a triangle, and the base and the height of that triangle are the two real numbers that I need to specify to know exactly where I am in the plane. Does that make sense?
Yeah.
So this is why we call it R2, because R2, we just need to specify an X and a Y, right? And then the set of all these points where X and Y are within the real numbers. So what this means is that this is a set of points. It's a set of points which are of the form X comma Y. So X and Y are both real numbers. It's basically the plane formed by all points of this form. Does that notation make sense, or is that?
You gotta
Re-explain it?
re-explain it real quick. Yeah.
Yeah, okay. So this means the set of, okay?
Okay.
So it's a collection of some objects. Now each of these objects I want to think of as just a point on the plane. So let's redraw the plane here. So I have a plane, okay?
Okay.
And if I take a point on this plane, if I specify, let's say I specify a point on this plane to be 0.
Okay.
Then any other point on the plane, I can essentially view it as, if this is a distance x and this is a distance y, I can view this point as essentially its horizontal distance from 0 and its vertical distance from 0.
Okay.
So let's draw this one more time. Let's draw it like on the board itself. So the board itself is a plane, okay?
Okay.
The board itself is a plane. Now I can specify that this is my point 0.
Yes.
I can just pick a specialized point like this. And I can draw a vertical axis and a horizontal axis. You with me?
Yeah.
Now, if you give me a point, you give me anything on this plane, any point here, okay? I can describe this point as x comma y. How do I describe it? Well, basically, I look at its horizontal distance from 0, that's x. I look at its vertical distance from 0, that's y.
Okay.
And then this point is described as that collection of information, x comma y.
Okay, yeah.
The plane itself is the set of all of points like that.
Okay.
So all of the points like that, where x and y, this just means x and y can be any real number.
Okay.
So x and y are real numbers. Then the collection of all these points is the plane. Yeah?
Yes.
And that we call R2. Okay?
Okay. Those are real numbers.
Yeah, so R2 is like R squared, right? I've taken a real line and I've turned it into a square. I've literally squared the real number. You see that?
Oh, yes. Yes.
Yeah.
Okay, that does make sense, yeah.
Yeah. So I've taken a one-dimensional line, turned it into a two-dimensional plane. That's why it's called R squared. And it's dimension 2, so this is the dimension. Okay?
Okay.
And then we can characterize this mathematically as the set of all these points, and each point has an x, has basically an x and a y. Okay, so you're with me there?
Yes.
So now let's think about R3 then. So how would you build R3?
R3.
Yeah, we just described R2 as being a plane.
What's
R3?
cube?
Yeah, the cube, right. Okay, pretty much exactly correct. So, three-dimensional space now, right? And we have 3 copies of the real line. Okay? And this goes out all the way to infinity, so this just goes all of space.
Okay, yeah.
Right?
Yeah.
Does that make sense?
Yeah.
And then the idea is that if I have a point if you give me a point in R3, this I'm going to call 0 here. If you give me a point anywhere in space, then I can look at this point and I can look at essentially its height. So its height is going to be some z here. So that's going to be on the z-axis. So here's our copy of R, which is vertical, and I can describe the point its height. And then above the point, I have it's also its x and its y here. Okay.
Okay.
So basically, to understand where this point is, I need to describe the projection of this vector here.
Yes.
Okay. So create a vector from the origin to this point. Now take this vector, project it onto this real line. When you project this vector onto this real line, you get the height. Okay? If you take this vector and project it onto this real line, you get the x-coordinate. And so by taking the vector of whatever point you gave me,
Yes.
and projecting it onto the x, y, and z axes, I can understand where it is. Basically, by looking at its shadow on the x, y, and z axes, I can understand exactly where this point is. And namely, it has coordinates x, comma, y, comma, z.
Okay.
Where these are the values of its projections. In other words, this is also what I'm saying.
Is Z, sorry.
Yeah.
But is Z a part of the real numbers or?
Yeah, so, great question. Yeah. So this is going to be the set of all points of the form x, y, z, such that, like you said, x, y, and z are real numbers.
Okay.
Okay?
Okay.
So I basically just added another label onto this thing that can vary. So now when you specify the location of a point in the room, right, if we were to specify the location of a point in this room,
Yes.
we would specify its height, and then we'd specify what point it was sitting above, basically, on the ground, right? we need to specify where on the ground it's sitting above. So if I want to describe the point of this eraser has a certain height. And then if I look at its shadow from a direct vertical light, its shadow on the floor, I can place the point on the floor, and that's just a point on a plane. So now I can specify the point on the plane as x comma y, and then the height as my z.
Okay.
As my z.
Yeah, that makes sense.
Does that make sense? Okay. And another way of saying this, let me just specify one last thing you could say, is that you can actually build this vector in space by first moving along x length, a length of x in this direction, then a length of y in the y direction, and then a length of z in the z direction. So x, y, and z both all encode a direction, right? X is this direction, y is this direction, z is this direction. So this point basically says that if I step a length of x in the x direction, and then I go a length of y in the y direction, and then I go a length of z in the z direction, I get the exact point in space that I want to describe.
Okay.
Make sense?
Yes.
And then in higher dimensions, it's going to be the same process where we can no longer visualize this because we're running out of dimensions here. We live in a three-dimensional world. Yeah, so this is n. N is any natural number. So it could be 2, 3, 4, 5, 6. Could be 1.
Okay.
Could be any natural number. So the natural numbers are 1, 2, 3, 4, 5, 6, etc. Okay?
Is it all just... Well, okay, I don't want to rush into negative numbers, so yeah.
Yeah. No, I mean, that's a good question. Could it be... So we consider R0
Okay.
to just be a point. So a zero-dimensional space is just a point. One-dimensional space, R1 is a line.
Okay.
R2 is a plane. R3 is space, etc. But R to the negative one, I don't know. That's a good question for the viewers, right? I don't know. That's a philosophical question. What's R to the negative? I don't know. But certainly this n here can be any natural number, okay?
Okay.
And the idea is, well, I'm going to need to specify n real numbers. So x1, x2, all the way down to xn. And when I specify these numbers, then, where x, i's are in R, if I specify all n of these numbers, then I know exactly where I am in Rn, okay? So, now, okay, let's look at one more example of Rn, okay? Let's look at one more example of Rn. Let's look at R4, okay?
Okay.
So, if we take a look at R4, how might we think to describe this? Well, one way you could say is let's specify 4 real numbers now,
Okay.
x, y, z, and t, such that all of these numbers are real numbers. Now, one way I can think about this is that every moment, I can think of this fourth coordinate as like time, okay? And then for any, so this t here, time is on a line now, so I can specify maybe like, this current time is time 0, and then maybe like, if I gave you t equals 3, that would be like 3 days into the future or something.
3 days. Okay.
Or you can say 3 seconds, it doesn't
3
matter.
seconds. 3
Once you
days.
specify a scale, it doesn't matter, right?
Okay.
But we need some sort of scale.
Okay.
And then maybe let's say x, y, and z are in feet, let's just say. So actually, yeah, let's say that these are, for example, of course they don't have to be this way, but just for example, these are all feet. And then t could be in seconds, let's say, okay?
Okay.
Now I'm going to specify, think of life as like a movie where each frame encodes a different space.
Okay.
So we have a family of spaces, of three-dimensional spaces, parameterized by time, evolving throughout time. So at every distinct time, there's a new space, okay? So to specify a four-dimensional object, I would specify its spatial location throughout all of time. Right?
Yes.
So for example, if I throw this eraser up and down, what does that look like in R4? So like at time 0, the eraser is here, and this is its spatial position in R3. Then at time t equals, some time step, it's now in this location. So think about the motion of the eraser
Yeah.
as split into a bunch of frames, like a movie.
Oh.
And those frames are evolving throughout time.
Yeah.
Okay? And so it's actually the entire time-like motion of this object is encapsulated in 4 dimensions. Okay? Does that make sense?
Holy shit. Yeah, that's insane.
Yeah. So, okay. So now but that's 4 dimensions. You can make it as many dimensions as you want, right?
Yes.
Okay, so that explains what Rn is.